In this video, we'll explore 5 key advantages of choosing a wireless infrastructure over wired installations. Industrial environments can be tough on cables and connectors. For example, the cables connecting a moving robot arm are especially vulnerable. They can get damaged from overuse, extreme temperatures, vibrations, collisions, or simply wear out. When a cable breaks, it can stop production, leading to lost time and money. Wireless connections offer a reliable solution to these issues, as they do not suffer from wear and tear like cables. By switching to a wireless alternative, companies can avoid unplanned downtime and maintain uninterrupted production. Using mobile robots, such as automated guided vehicles, AGVs, or autonomous mobile robots, AMRs, improves efficiency and safety by automating the transport of materials. This reduces human error and risk of accidents. Due to the machine's mobile nature, wireless technology is essential for communication with other factory systems, such as fleet managers or safety protocols. To comply with stringent EU safety requirements, the best way to connect emergency stops or e-stops to AGVs or AMRs is through wireless technology. Moreover, wireless technology enables companies to access data easily and safely. Devices such as handheld HMIs allow you to quickly and conveniently check equipment without needing to physically connect to machines or enter unpleasant or potentially hazardous environments. In addition, wireless is quicker and cheaper to install, with no need for long runs of expensive cables. It also provides the flexibility to move or adjust installations. In this video, we'll provide a brief overview of Bluetooth, Wi-Fi, and cellular technologies, highlighting their capabilities in terms of range and throughput. Let's start with Bluetooth, which offers low bandwidth, low power consumption, and short range. Bluetooth Class 2 and 3 are common in consumer electronics, with the range 1 to 10 meters. In contrast, Bluetooth Class 1, used in industrial applications, supports up to hundreds of meters. The different Wi-Fi generations offer higher bandwidth, increasing by generation. Wi-Fi 4 has a theoretical bandwidth of hundreds of megabits per second. Wi-Fi 5 is even faster and allows for more robust internet usage, including streaming and gaming. Notably, Wi-Fi 6 is almost 3 times faster than Wi-Fi 5. Moving on to cellular technologies, LTE M1 and NB-IoT are ideal for low-power wide area, or LPWA, applications, offering several kilometers range. For applications requiring more bandwidth, such as functional safety, cellular offers 4G LTE and 5G. 4G LTE theoretically provides bandwidth up to 1 gigabit per second, whereas 5G can offer bandwidths of several gigabits per second, depending on the frequency band it operates on. Please note that bandwidth varies due to factors such as range, signal strength, interference, device capabilities, and network congestion. In reality, the actual speed is significantly lower than the theoretical maximum bandwidth. Another important distinction between the different technologies is the frequency bands they use. Cellular networks use licensed frequencies, ensuring exclusive and reliable communication. However, it can also incur significant costs for users. In contrast, Bluetooth and Wi-Fi operate in unlicensed bands, which is cheaper but may be more congested due to open access. These are some of the differences in wireless technologies. For a more in-depth understanding, please enroll in the specific e-learning course for each technology. In this video, we'll clarify some key wireless terminology. Terms covered are electromagnetic waves and spectrum, frequency and wavelength, microwaves and ISM bands, and modulation. In wireless communication, electromagnetic waves are used to transmit data through the air without the need for physical connections like cables or wires. The waves are a form of energy that travels through space and can carry information. There is a whole spectrum of electromagnetic waves ranging from the longest and low-energy waves used for radio broadcasting to the shorter, high-frequency waves in ionizing radiation. The spectrum is divided into regions, each characterized by different wavelengths, frequencies, and potential applications. For example, radio frequency is primarily used to transmit information. This can be through radios, Bluetooth, Wi-Fi, cellular, and even satellites or GPS. Radio frequencies are also used in radars, alarm systems, and material measurements, as well as for heating in a microwave oven. At the center, we have the light, which includes infrared, visible light perceived as colors, and ultraviolet light. Finally, the high-energy waves of ionizing radiation are potentially hazardous and can cause cell damage, applied in, for example, medical radiotherapy. Before focusing on the microwave spectrum, where most of the industrial wireless technologies operate, let's clarify the terms wavelength and frequency. The wavelength is how long one wave is and is measured in meters. For example, visible light has wavelengths from 380 to 700 nanometers, whereas the wavelengths in the microwave spectrum are 1 millimeter to 1 meter. Frequency is how often a wave cycles per second and is measured in hertz. For example, Bluetooth and Wi-Fi operate at 2.4 gigahertz. Wi-Fi can also operate at higher frequencies, such as 5 or 6 gigahertz. The wavelength and frequency of a wave are inversely related, and the relationship is expressed with this formula. The wavelength, represented by lambda, equals the speed or velocity of the wave divided by its frequency. The velocity of any electromagnetic wave is approximately the speed of light, which is around 300,000 km per second. Note that lower frequencies like AM and FM radio signals travel longer distances and can penetrate objects, such as buildings, more effectively. This is why they're used when signals need to cover a large area. On the other hand, technologies like Bluetooth and Wi-Fi use higher frequencies, such as 2.4 or 5 gigahertz. These signals have shorter wavelengths, which means they cover less distance and have less penetration capacity. However, they offer higher data throughput and reliability than radio signals, which are crucial for certain applications. Another interesting fact is that the lower frequency signals can follow the Earth's curvature. This isn't the case for higher frequencies, where the signals travel in a straight line or line of sight. Now, let's have a look at the part of the electromagnetic spectrum known as microwaves. This is where most industrial wireless technologies operate. The microwave spectrum spans from 300 MHz to 300 GHz. Bluetooth and Wi-Fi operate on frequencies known as industrial, scientific, and medical, or ISM bands, which are free for anyone to use. Let's have a look at the 2.4 GHz ISM band, where both Bluetooth and Wi-Fi operate. At this frequency, other devices such as microwave ovens or alarm systems also operate. This might cause interference, which is important to consider when setting up Wi-Fi networks. To avoid interference, other ISM bands at the ranges of 5 and 6 GHz could be used, since these are less crowded. Now, how does an electromagnetic wave transfer information? This is achieved using a technique called modulation. Here are 4 examples. In Morse code, we simply turn the signal on and off. In amplitude modulation, or AM, used in radio broadcasting, we alter the strength or power of the signal. Whereas in frequency modulation, or FM, we change the frequency of the signal. Most modern technologies, such as Wi-Fi and cellular networks, use more complex modulation techniques to send digital information. One such technique is phase shifting. In this video, the terms latency and jitter are explained. Latency is the time it takes for data to travel from one point to another in a network. It's usually measured in milliseconds and represents the delay or lag experienced during data transmission. When latency is low, it means there's a shorter delay. This leads to faster response times and improved real-time communication experiences. For instance, you might notice smoother video streaming and quicker web page loading. The term jitter refers to variations in latency. If jitter is high, frames might arrive out of order, which can disrupt the flow of data. Note that as long as latency is consistent and not too high, slightly higher latency is usually not a problem. For example, the latency in Bluetooth is higher than in Wi-Fi, but since jitter is low, this will not cause an issue. Both latency and jitter are generally lower in 5G compared to other wireless technologies. Wi-Fi 6 and Wi-Fi 6E have improved latency and jitter performance. However, they can still be affected by interference from other devices, which might increase jitter.